Okay, and so acceleration and all of these equations that go with acceleration are what our focus is going to be today. So we need to note that acceleration is any sort of change in velocity. It could be speeding up or slowing down could be considered an acceleration. And that's a little bit counterintuitive for us because we have used the word acceleration to always mean speeding up. Okay, but that's not the case. Any sort of change in velocity is considered an acceleration. Okay, acceleration can be positive or negative. It can be positive or negative. We looked at our little rule of thumb. Do you remember our rule of thumb for positive and negative acceleration? That's with velocity, positive, negative. But we said if something is slowing down, the sign of our acceleration and our velocity are opposite of each other. Okay? So here it is. If you don't have it written down, write it down now. If you are slowing down, the acceleration is opposite the direction of the motion. If you are slowing down, the acceleration is in the opposite direction of the motion. So I'm going to show you that on a graph quickly, just to look at it one more time. Here's velocity, here's time. Okay? If I'm slowing down in the negative direction, my graph looks like that. Do we agree? That red line is slowing down in the negative direction, which means I have negative velocity. We agree with that? Because we are below the x-axis. Yet the slope of my line, which is acceleration, is it positive or negative? Positive acceleration. Okay, because I am slowing down, I have an acceleration and a velocity that have opposite signs. Okay, and so I'm going to prove that to you mathematically as well. Okay, using this equation right here. This equation should go on your equation sheet. Okay, the line over my A here just means average. You will never see me write that over the A again. Okay, it's like that in your book, so I show it to you once, but I never will write the line over the A again, so don't feel like you have to write that on your equation sheet. Okay, but the way we solve for acceleration is the change in velocity over change in time. So I'm going to prove this rule of thumb to you mathematically as well. What does the delta mean? Good. Change in. Or it always means final minus initial. Okay, so I'm going to give you an example here that looks like our graph. Let's say that my initial velocity is negative 10 meters per second, and my final velocity is 0, right? Would you believe me that I'm slowing down there? Going from negative 10 to 0. Let's say that it took me 5 seconds to do it. So if I'm going to solve for my acceleration, I would say A equals final velocity minus initial velocity. Sorry, let me get rid of this circle right here. Final velocity minus initial velocity over time. Agreed? And so what happens on my numerator? What needs to happen there to those two negatives? They become positives, right? If I subtract a negative, that becomes a positive. We agree with that? So my acceleration is positive 2 meters per second squared.
Is acceleration always squared?
Meters per second squared. It's the unit that is squared. The number itself is not squared. So if I take meters per second, which is velocity, divided by seconds, I get the units meters per second, which is the same as meters per second squared. So that is the units for acceleration always. Okay, so if you don't have those units written down, maybe write those down. Okay, meters per second squared. That's an indicator for you in a word problem that value is your acceleration. Okay, you need to be able to pick out variables based on their units. Okay, and we'll look at that here in just a second. It's like I can read my mind. Okay, units are meters per second squared. Okay. During a race, a sprinter increases from 5 meters per second to 7.5 over 1.25 seconds. What's the sprinter's average acceleration during this period? Okay, you don't have to write out the whole question. If you feel like you want to, that's fine, but I'm usually not going to wait for you to write out the whole question. So I'll give you about a minute or so to get down what you need, and then we'll start working this together. I will always recommend, regardless of the difficulty of the problem, which this problem is not very difficult, okay, what I'll always recommend is to write your variables in the margins. Okay, so we'll make a list of our variables in the margins. This, tell me, is this velocity, is this acceleration, is that time, is it distance? What is that 5 meters per second telling us? Velocity, good, because it's meters per second. That's the unit for velocity. And is it my initial velocity or my final velocity? Initial, right? Because it tells me I go from 5 to 7.5. So what I'm going to do is I'm going to make my list. VI equals 5, VF equals 7.5, and then what other variable do I have? I have 1.25, which is what? Time, right? I know this seems simplistic, like why do we need to do this? But when we start solving problems with 8, 9 variables, we need to be able to be organized in solving that. So I always like to also put in, I'm solving for acceleration, so that's my question mark. Right? I like to write down, what am I solving for? So that I can go to my equation sheet and I can say, what equation has all these variables that I have or need in it? Okay, and so our answer is that. Acceleration equals, is it 5 minus 7.5? Right. 7.5 minus 5 over 1.25. Okay, 2.5 over 1.25. So my acceleration is 2 meters per second squared. Do we agree? Are we speeding up or slowing down? We are speeding up in the positive direction. So my acceleration should be positive or negative? Positive, because I'm speeding up. Very good. Okay, questions about that? Yeah.
In the last problem, why was it?
This is a negative. I don't know why it didn't carry over, but here's our negative 28.6. It's not just like a dash. Like this is supposed to be my negative. I need to fix that. Sorry. Okay, never mind. I tried to edit it from there, but I can't do that.
Can it be a decimal?
It can. Okay, good. Velocity and acceleration, I just want you to listen through this. You don't have to necessarily write it down. Velocity and acceleration are not the same thing. Velocity tells me the rate at which my what changes? Nope. The rate at which my displacement changes. Velocity tells me how fast am I changing positions. But acceleration tells me what? How fast I'm changing speed or velocity, right? The rate at which my velocity is changing. Okay, so velocity tells us how fast our position changes. Acceleration tells us how fast our velocity is changing. So if our acceleration is 1 meter per second squared, that means for every second that goes by, my velocity is getting faster by 1 meter per second, right? That's what that means. Okay, I don't want to do that one. All right. With a partner, I want you to think about this question. If the acceleration of an object is 0, does it mean that the velocity is 0? Think about that question with your partner. I think I just have one. Okay, don't talk too loud. Think about it with your partner. We're going to discuss and come back in about 30 seconds. Kina usually means what? Okay, kinetic, but that usually means motion, right? Kina means motion, that prefix. So kinematics equations for constant acceleration. None of these equations are valid unless we know we have constant acceleration. Constant acceleration. This equation needs to go on your equation sheet, for sure. This is the first of the big three. Okay, so I gave you just these little quarter sheets of paper to write equations on. That's all it is. Just so that you can have it out when you're doing homework rather than flipping through notes. Okay? So you can look at the ones Maddie has on here and put those on there. So when we say constant acceleration, I mean that we cannot solve a problem that says, I stayed still, and then I sped up for 10 seconds, and then I slowed down for 5 seconds, then I sped back up. We can't solve that in one equation. We have to break that up into its sections of equal acceleration, of constant acceleration. So if we have motion that is complex, where we speed up and then slow down and then we do something else, we take several different equations to help us solve that. Okay? So here's our first one. VF tells us final velocity, VI is initial velocity, A, and T. This equation, believe it or not, is exactly like the one you just learned, except rearranged. If I take A equals VF minus VI over T, and I rearrange that equation, times T, that gives me VF minus VI equals AT, and I add VI over to the other side, VF equals VI plus AT. Right? It's the exact same equation, just rearranged. Okay? So you can use either of these equations if you have those 4 variables. You'll see me use this one much more often. Okay, so that delta A, delta V equation, we don't use it all the time, I use this one.
So what is it used to find?
Any of these 4 variables.
Okay.
Any of these 4. Right, you'll be given 3, you'll be asked for 1, and you would use that equation. Okay, so we're going to practice some with this. A bus traveling 30 kilometers per hour speeds up at a constant rate of 3.5 meters per second squared. What is its velocity at 6.8 seconds later? So I'll give you about a minute or 2 to get written down what you need, and then we'll work it out together.
3.5 meters per second.
Okay, 3.5 meters per second squared. What value is that? What variable? A. There should be something else that's sticking out to us as odd or not matching. Right, 30 kilometers per hour. Is that my initial velocity or my final velocity? Initial. And can I use those values in the same equation? I cannot. I cannot plug in kilometers per hour and then meters per second squared into the same equation. My units have to match. So what's my shortcut to go from kilometers per hour to meters per second? Good. Divide by 3.6. Okay, that's my shortcut to go from kilometers per hour to meters per second. If you don't remember that shortcut, you can always solve it using a T-chart, but that's going to save you a lot of time. Okay, so kilometers per hour to meters per second. 8.33. So that's my initial velocity. Okay. I've got a time of 6.8. And I'm solving for what variable? V, F, right? That's my question mark. Okay, so then I plug the numbers in. That's it. Okay, VF equals 8.33 plus 3.5 times time. So go ahead and plug that in. Tell me what you get. Okay. 32.13 meters per second. Seem easy enough? Okay, the important part there is that you had to recognize that a conversion was needed. Okay, we have to be able to see that. All right, here's our second equation. Second of the big 3. Okay, these are our kinematic equations. This is the second one. It needs to go on your equation sheet. Gets a tad more intense than the first. All right, XF, that stands for our final displacement. XI is initial displacement, and the rest are familiar to us. Something that I want to point out here is that in this equation, only the t is squared. Okay, only the t is squared, not the whole term, just the t. So 1/2 a t squared. Okay, you can put parentheses around it if you need it. I won't write it that way, but only the t variable is squared. Down here at the bottom, there's a little note that says most of the time x sub I can be set to 0 since it's a starting location. You will see me solve almost all problems that way, right? I told you at the beginning of the year, we set our origin at the beginning of the motion, which means we're starting our motion at 0. That's going to be the case a lot of the time. Okay, so here we go. Maybe. In an emergency, a driver brings a car to a stop in 4 seconds. The car is initially traveling at 25.24. What's the car's acceleration, and how far does it travel before coming to a complete stop? Okay, we've got 2 different questions we need to answer here. 2 different questions we should answer. I'm going to go ahead and start writing out my variables to the side. What are some variables that I know? Jimmy, what's one variable that I know from my problem? Like initial velocity, final velocity, time, acceleration. What? Give me one of them. This number right here, what does it tell us? Time, right. We're going to pick a number and look at its unit, right? This is measured in seconds, so that means time is 4. Okay, this velocity right here, is that our initial or our final? Initial. So v sub I equals 25.24. What does our final velocity give us? 0. How do we know our final velocity is 0? It comes to a complete stop. Okay, we want to find acceleration, and what's the second variable we want to find?
Distance.
Right, distance. Okay, and so I'm going to say that's x. Do we want to find x initial or x final? Final, right? I'm going to assume that x initial is 0. Because we're looking at the part of our motion from when the braking begins to when it comes to a stop. Okay, so those 4 seconds are all we're paying attention to. So we don't care how far the car traveled before that time, right? All we're looking at is the 4 seconds to the stop. And so we're saying from that position, which we'll call 0, how far did they travel? Does that part make sense? Okay, which do I need to solve for first? Can I solve for x sub I before I solve for acceleration? No, because isn't acceleration in that x kinematics equation? Yeah. So I need to solve for acceleration first. So I would say 0 equals 25.24 plus a times t. Mathematically, how do I solve for a here? How do I solve for a? Mathematically, what do I need to do? I need to, right, I need to subtract this over first and then divide by 4. So that'd give me negative 25.24 equals 4a. Divide by 4. And tell me what my acceleration should equal. Yeah.
What if you did the v over t?
That's fine. Mathematically, it's exactly the same. In the second equation, so we're using our VF equals VI plus AT equation because we can't solve for x yet without having acceleration. Yeah, good question. So our acceleration equals what? Good. Negative 6.31. Does it make sense to us that our acceleration is negative? Is that consistent with our rule of thumb? We are moving in the positive direction and slowing down, so our acceleration should be negative. Good.
I didn't get it.
You didn't get that answer?
No, I got that answer. I didn't get negative.
So if you're doing VF, you're doing the over.
Yeah, I did A equals V over T.
Okay. So did you do 0 minus 25.4 over T? Right, because 0 is our final velocity, so it's always final minus initial. Okay, second part of our problem, I need to solve for x final. So I'm going to use that xf equals xi plus vit plus 1/2 at squared equation. Okay. X final is what we're solving for. My initial position is 0. Initial velocity is 25.24 times my time plus 1/2 negative 6.314 squared. Go ahead and get that plugged in and let me see what you got. Answer, so I'm assuming that's right. 50.48 meters.
I didn't get that one.
Okay. Okay, let's see here. I'll rewrite it if you want, but VF squared equals VI squared plus 2A times delta X. Okay, or you could write it as X final minus X initial if that feels better. If you don't like the delta, you could write it that way so you see all your variables. What variable is this equation missing? It does not have time. So this would be an equation you could use if you're not given time in your equation, right? You don't have to waste time solving for time and then going back, right? You don't have to use time because this equation doesn't have it in there. The second equation I gave you, what was it missing? Look back at the second one. What's it missing? Velocity final, right? So I can use that equation if I'm not given a velocity final. So there's ways that you can just stick to one equation. All right, let's try one here. Car starts at rest and speeds up at 3.5 meters per second. How far will it have gone when it's traveling 25 meters per second? Right. Good. I heard somebody say it. Starting at rest means our VI is equal to 0. This 3.5 value is acceleration. Good. How far will it have gone? That means I'm solving for X final. Good. My X initial, I'm going to always call 0 because I'm only looking at the start of the motion. My final velocity is 25. Right, positive 25. It's going forward. So if I didn't know what equation I was using, right, considering I just gave you number 3, that's what we're going to use. But if I didn't know, I would look at my list and I would say I don't have time. Right? I could use the first equation and solve for time, then use the second equation and solve for X final, but that's too much work, right? I have number 3 that allows me to solve for these variables without time, so that's what I'm going to use. 25 squared equals 0 squared plus 2A X final, right? And it's really X final minus 0, so I'm just going to leave that off. Right, because my initial position is 0. Does that part make sense? What's the value for 25 squared? I don't know what that is. Okay, that's what I thought. Okay, wow. 7x final right? That 0 squared gets dropped. 7 times xf divided by 7, and I get a final displacement of,
89.2. Well, 29.
that's fine, 89 point something meters. We agree there?
Yes.
Okay, how are we feeling about using the equations? Like out of 5, give me a 5. Like 5, I'm awesome. 1, I have no idea what you're talking about.
Way better than that.
Okay, good. How do we feel about picking the equation by yourself? Are we a little more nervous about that? No, feeling good? Okay. All right. Well, yeah, you can use your sheet all the time, but sometimes it's a little hard if I don't tell you what. Yeah, you'll always get your sheet. Try this one on your own. I'm not telling you what equation you should use.
Okay.
The fact that I said that maybe is a little hint.